in structure. Some researchers propose that the formation is an optical illusion, where a more cylindrical or bipolar outflow appears squared due to our viewing angle. Others argue that external influences, such as a dense interstellar medium or remnant stellar winds, may be reinforcing the shape by constraining material along specific planes. Advanced telescopes equipped with high-resolution spectrographs are expected to provide more precise data on the velocity distribution of gas and dust. By analyzing how light interacts with different regions, astronomers hope to reconstruct the three-dimensional shape and determine whether the observed symmetry is an inherent property or a temporary phase. If the central star is approaching a supernova event, its surrounding nebula could dramatically brighten as the explosion interacts with the ejected material, similar to what has been observed in other massive star systems. Comparisons to other structured nebulae suggest that mass loss in massive stars follows patterns that are more organized than previously thought. While planetary nebulae often display symmetric forms due to the expansion of shells around dying stars, this particular object exhibits a level of precision that challenges conventional models. If magnetic forces are indeed playing a dominant role, it may suggest that similar structures could exist elsewhere but remain undetected due to their orientation or distance from Earth. Infrared observations have also hinted at the presence of complex organic molecules within the nebula, which could have formed through photochemical reactions triggered by high-energy radiation. Such environments are thought to be crucial in the early stages of planetary system development, as they contribute to the formation of prebiotic compounds that later become part of interstellar dust clouds. Understanding how these materials evolve in different stellar environments provides insight into the chemical diversity of the galaxy. Future research will focus on mapping the precise movement of gas within the nebula and determining whether external factors are influencing its evolution. If a binary companion is confirmed, it could provide further evidence that multiple star systems are a key factor in shaping structured nebulae. Long-term monitoring may reveal subtle shifts in brightness or morphology, indicating ongoing dynamic processes that have yet to be fully understood. If the central star eventually undergoes a supernova, it could transform the surrounding region by sending shockwaves through the nebula, triggering secondary reactions and possibly altering its structure. The resulting supernova remnant would provide valuable data on how pre-existing mass loss affects the aftermath of stellar explosions. If a neutron star or black hole forms at the core, it may interact with the surrounding material in ways that produce additional high-energy emissions, making it a potential source of radio waves or X-ray bursts. The precision of the formation continues to challenge existing astrophysical models, suggesting that either previously unknown mechanisms are at work or that magnetic shaping plays a far greater role in stellar evolution than currently assumed. Upcoming telescopes with adaptive optics and interferometry will provide deeper insights into the processes governing the expansion of ionized gas and the interaction between radiation and dust within the nebula. While its ultimate fate remains uncertain, its significance as an astrophysical case study is undeniable. Whether it is a short-lived phase of stellar evolution or a long-standing feature that will persist for thousands of years, it represents a rare and valuable opportunity to study the forces that shape the most massive stars in the cosmos. The answers it holds could refine our understanding of how stars evolve, how they lose mass, and how they influence the galactic environment over cosmic timescales. The forces responsible for shaping this nebula remain a subject of debate, with multiple mechanisms potentially working in tandem to maintain its strikingly structured form. The presence of a dense circumstellar medium suggests that earlier mass ejection events may have interacted with surrounding material, creating shock fronts that reinforced the observed geometry. If stellar winds or episodic eruptions from the central star were directed by an unseen companion, their effects could have compounded over time, gradually sculpting the nebula into its current configuration. Magnetic fields are another possible factor influencing its development. In some high-energy astrophysical environments, magnetic pressure can guide ionized gas along preferred paths, constraining outflows into collimated jets or symmetric lobes. If this phenomenon is occurring here, it could help explain the sharp definition of the nebula's edges and the near-identical structure on opposite sides of the central star. Observations of other massive stellar remnants have shown that even weak magnetic fields can have a profound impact on outflow dynamics, reinforcing the idea that this nebula's shape may be magnetically driven. The chemical complexity of the surrounding gas adds another layer of intrigue. The discovery of molecular hydrogen and polycyclic aromatic hydrocarbons within the nebula suggests that the region has undergone prolonged exposure to ultraviolet radiation, leading to chemical reactions that produce complex organic compounds. If this material later becomes part of interstellar clouds, it could contribute to the formation of planets or even prebiotic chemistry in future stellar systems. This highlights the role of evolved stars not only as sources of heavy elements but also as potential contributors to the early chemistry of planetary environments. The velocity distribution of ejected material is also a critical factor in understanding the formation of the nebula. If the gas is expanding uniformly, it would suggest that the star has been losing mass gradually over an extended period. However, if velocity gradients are detected, with some regions moving faster than others, it could indicate episodic bursts of energy, possibly linked to a hidden binary companion or internal stellar instability. High-resolution spectroscopic studies will help determine whether the structure has remained stable or if it is actively evolving, with changes in brightness or morphology providing additional clues. Comparisons to other known stellar outflows provide valuable context for interpreting this structure. The similarity to bipolar planetary nebulae, which are often shaped by binary interactions, suggests that the nebula may represent an earlier stage of this process in a much more massive system. If future observations confirm the presence of an orbiting companion, it could provide strong evidence that binarity is a key factor in the formation of highly structured nebulae, challenging existing models of single-star mass loss. The possibility that the central star is approaching a terminal supernova phase adds an additional layer of urgency to ongoing research. If this is a pre-supernova system, then the surrounding nebula may play a crucial role in determining the characteristics of the eventual explosion. A dense circumstellar medium could shape the supernova's light curve, producing an extended afterglow or even influencing the type of remnant that forms. If the core collapse results in a neutron star or a black hole, the interaction between the compact object and the surrounding nebula could generate secondary emissions, including high-energy X-ray or radio bursts. Some researchers propose that this nebula represents a previously unrecognized category of structured stellar outflows, distinct from both planetary nebulae and classical supernova remnants. If so, it could mean that highly organized mass loss occurs in more stars than currently expected but remains undetected in systems with less favorable viewing angles. Advanced three-dimensional modeling, combined with data from next-generation telescopes, will be necessary to determine whether similar formations exist elsewhere in the galaxy. Long-term monitoring will be essential to track any changes in the nebula's structure. If subtle shifts in brightness or gas distribution are detected, it could indicate ongoing mass loss or dynamic interactions within the expanding material. Alternatively, if the nebula remains unchanged over decades of observation, it would suggest that its formation was driven by a past event rather than active processes occurring in the present. Either scenario will provide valuable insights into how massive stars shed their outer layers and how those layers evolve over time. The nebula's role in the broader astrophysical landscape extends beyond its immediate surroundings. If it is indeed an example of a structured pre-supernova outflow, it could help refine predictions for other massive stars nearing the end of their life cycles. Understanding the processes shaping this formation could improve models of how supernovae interact with their environments, potentially leading to better interpretations of historical supernova remnants observed throughout the galaxy. Future research will focus on uncovering the underlying drivers of the nebula's symmetry, whether they be magnetic forces, binary interactions, or unknown stellar dynamics. Upcoming missions and observational campaigns will provide increasingly detailed data, helping to answer fundamental questions about the role of evolved stars in shaping the structure of the interstellar medium. Regardless of what mechanisms are ultimately responsible, the nebula remains a rare and invaluable opportunity to study the complex interplay between stellar evolution, mass loss, and the physical forces that govern the cosmos. As observational techniques continue to improve, new details about this enigmatic formation will likely emerge, shedding light on the precise mechanisms responsible for its near-perfect symmetry. The role of radiation pressure in shaping the expanding gas is an area of active investigation, as intense stellar winds could be driving material outward along well-defined paths. If the star is emitting energy anisotropically, with stronger radiation in specific directions, it could be influencing the way ejected material disperses into space. This could help explain the structured nature of the nebula, particularly if interactions with a surrounding dust disk or magnetic field are reinforcing its geometric appearance. High-energy phenomena may also be contributing to the evolution of this structure. Some researchers suggest that the presence of shock fronts, regions where fast-moving gas collides with slower material, could be shaping the expanding nebula. These interactions create areas of increased density and ionization, altering how light scatters and giving the nebula its distinctive brightness distribution. If these shocks are being driven by periodic stellar outbursts, then the formation could be the result of multiple ejection events over time, each adding to the overall complexity of its structure. Infrared observations continue to provide new insights into the dust and gas composition of the surrounding environment. Data suggests that the dust grains within the nebula are relatively large compared to those found in diffuse interstellar clouds, possibly indicating that they have undergone significant processing due to radiation collisions. If this region is rich in carbon-based compounds, it could support the idea that evolved stars contribute not only to heavy element enrichment but also to the formation of molecular precursors essential for planetary system development. Determining the precise age of the nebula is another critical aspect of ongoing research. By analyzing the expansion velocity of different gas layers, astronomers aim to estimate when the initial mass ejection occurred. If the nebula is relatively young, it could be the result of a recent instability in the central star, whereas an older formation would suggest a more gradual mass loss process over an extended period. This distinction is important in understanding whether this structure is a transient phase that will evolve into a more diffuse remnant or if it represents a long-lived phenomenon sustained by continuous energy input. The potential presence of a binary companion remains a crucial question, as its conformation would provide a strong explanation for the nebula's ordered structure. If a secondary star is orbiting the central object, its gravitational influence could be directing material into specific flow patterns, producing the observed symmetry. Some models suggest that if a white dwarf, neutron star, or even a black hole is present, accretion-driven outflows could be responsible for the formation's striking shape. Identifying subtle variations in the motion of the primary star or detecting indirect signs of a hidden companion through X-ray or radio emissions may help resolve this mystery. Further study of the polarization of light from the nebula will be useful in determining whether magnetic forces are playing a significant role in its evolution. If light scattering patterns indicate the presence of aligned dust grains, it could suggest that a strong magnetic field is guiding the expansion of gas. Such a scenario would align with models of magnetically collimated outflows, which have been observed in other astrophysical environments, including young stellar objects and active galactic nuclei. One of the most intriguing possibilities is that this formation represents an early stage of a process that has not been widely documented in astrophysics. If it turns out to be a precursor to a more well-known structure, such as a planetary nebula or a supernova remnant, it could provide a unique opportunity to study how these phenomena develop over time. Observing how the nebula changes in the coming years will be crucial in determining its future trajectory, whether it will eventually dissipate into the interstellar medium or continue evolving into a more complex structure. If the central star ultimately undergoes a supernova, the surrounding material could play a key role in shaping the explosion's observable characteristics. The presence of dense circumstellar matter could cause significant interaction between the supernova shockwave and the pre-existing nebula, leading to an unusually bright and prolonged event. If this occurs, it could offer direct observational evidence of how mass loss influences the final stages of massive star evolution. Long-term monitoring with next-generation telescopes will be essential in answering the remaining questions surrounding this extraordinary structure. Instruments capable of resolving fine details in the gas distribution, magnetic field orientation, and spectral properties will provide the data needed to construct a more complete picture of its origins and evolution. If similar objects are identified elsewhere in the galaxy, it may indicate that these types of structured outflows are more common than currently believed, potentially leading to a re-evaluation of existing models of stellar mass loss. Regardless of its ultimate fate, this nebula remains one of the most visually striking and scientifically valuable examples of how complex forces interact in the late stages of stellar evolution. Whether shaped by binary dynamics, magnetic fields, episodic outbursts, or a combination of multiple factors, its existence challenges conventional astrophysical theories and offers an unparalleled opportunity to study the intricate processes governing massive stars. Future observations will undoubtedly bring new discoveries, deepening our understanding of how these cosmic structures form, persist, and eventually transform into the next generation of celestial phenomena. As observations continue to refine our understanding of this extraordinary formation, the interplay between multiple astrophysical forces becomes increasingly apparent. The near-perfect symmetry suggests that a finely tuned combination of stellar winds, radiation pressure, gravitational dynamics, and possibly magnetic confinement is at work. Each of these factors contributes to shaping the expanding shell of gas and dust, maintaining its structural integrity over time. Whether this level of organization is an inherent property of certain types of stellar outflows or a rare coincidence of conditions remains an open question. Infrared spectroscopy has revealed variations in the temperature and density of different regions within the nebula, indicating that it is not a uniform shell but rather a complex, layered structure. This suggests that multiple ejection events may have occurred at different times, each adding a new component to the overall formation. If past eruptions have been episodic, possibly regulated by internal instabilities in the central star or interactions with an orbiting companion, the nebula could be an evolving record of its progenitor's mass loss history. The detection of specific ionized elements in the surrounding gas suggests that high-energy radiation from the central star is actively altering its chemical composition. Regions exposed to the most intense ultraviolet and X-ray flux exhibit signs of ionization-driven molecular dissociation, while more shielded areas retain heavier molecules and dust grains. This dynamic environment provides insights into how massive stars influence their surroundings, gradually enriching the interstellar medium with elements forged in their interiors. One of the primary challenges in understanding the nature of this structure is determining whether its symmetry is a transient feature or a long-term characteristic. If it is the result of a recent outburst, it may slowly degrade over time as the expanding material interacts with external forces. On the other hand, if it is stabilized by ongoing processes, such as a sustained mass flow or a persistent magnetic field, its geometry may remain largely unchanged for thousands of years. Tracking subtle shifts in the nebula's brightness and morphology over successive observational periods will be essential in distinguishing between these possibilities. Comparisons to other known examples of structured nebulae suggest that ordered mass ejections are more common than previously assumed. However, the degree of symmetry observed here is exceptionally rare, indicating that specific conditions must be met for such formations to arise. If future surveys identify similar objects in different regions of the galaxy, it could provide a broader statistical foundation for understanding how often these structures occur and what factors contribute to their development. Advanced numerical simulations are being used to model the potential formation scenarios for this system. By incorporating variables such as stellar rotation, pulsation-driven mass loss, and binary interactions, researchers hope to replicate the observed structure and determine which forces dominate its evolution. Early results suggest that a combination of rapid stellar rotation and a companion's gravitational influence could create flow patterns that resemble the nebula's distinct shape. If these models prove accurate, they could offer a new perspective on the role of binarity in shaping circumstellar environments. Another intriguing aspect is the potential for future variability in the central star itself. If it is nearing the end of its evolutionary cycle, further instability may lead to additional mass ejections or luminosity fluctuations. Such changes could provide direct observational evidence of how the formation is being influenced by ongoing stellar processes. If a sudden brightening event occurs, it could be a sign of an impending transformation, possibly signaling the transition into a Wolf-Rayet phase or even the approach of a terminal explosion. If the star ultimately undergoes a core-collapse supernova, the surrounding nebula could play a critical role in shaping the aftermath. A dense pre-existing medium could result in an unusually energetic explosion, with shockwaves producing intricate interaction patterns within the already structured outflows. Such an event would be a rare opportunity to observe how massive stars influence their own supernova environments, offering insights into the processes that govern the final stages of stellar life. Long-term monitoring efforts will focus on detecting changes in expansion velocity, ionization levels, and thermal emissions within the nebula. Any deviations from the expected behavior could indicate previously unknown influences at work, potentially revealing new physics governing stellar outflows. With upcoming space-based and ground-based observatories providing increasingly detailed data, a clearer picture of this remarkable formation will continue to emerge. Whether this structure is an exceptional case or part of a broader, yet underappreciated category of organized mass ejections, its study is reshaping perspectives on how stars interact with their surroundings. The precise forces maintaining its near-perfect symmetry remain one of the most compelling mysteries in modern astrophysics, and future discoveries may provide the missing pieces needed to unlock its true nature. Regardless of what new revelations come to light, this nebula stands as a striking testament to the complex and often unexpected beauty of stellar evolution. The persistence of such a structured formation raises fundamental questions about the longevity of ordered nebulae and the mechanisms that sustain their geometry over time. If the observed symmetry is not merely a transient effect, then ongoing processes must be actively maintaining its precise form. One possibility is that the radiation pressure from the central star is continually shaping the expanding gas, reinforcing existing structures and preventing dissipation. In this case, variations in stellar output could lead to subtle but measurable shifts in the nebula's morphology, offering insights into how radiation-driven mass loss influences circumstellar environments. The presence of complex molecular compounds within the expanding shell suggests that chemical evolution is occurring on a large scale. As ultraviolet and X-ray radiation interacts with dust and gas, it triggers photodissociation processes that break apart existing molecules and encourage the formation of new ones. This cycle of destruction and recombination is key to understanding how massive stars contribute to the molecular diversity of interstellar space. If the conditions within the nebula are stable enough, they may support the gradual synthesis of increasingly complex compounds, further enriching the surrounding medium. Velocity mapping of the nebula's outflows is another avenue of investigation that may yield crucial insights into its formation history. If different layers of gas are expanding at distinct rates, it could suggest multiple episodes of mass ejection, each contributing to the overall structure. By reconstructing the motion of individual gas clouds within the nebula, astronomers can determine whether the expansion is accelerating, slowing down, or maintaining a steady rate. A uniform velocity distribution would support the idea of a single, well-coordinated outflow event, while irregularities could indicate ongoing dynamic interactions between different layers of material. The role of external influences, such as interactions with the surrounding interstellar medium, is also worth exploring. If the expanding nebula is encountering regions of higher density gas, it could be experiencing external pressure that helps define its shape. This scenario is particularly intriguing because it would imply that the large-scale structure of the interstellar medium plays an active role in shaping stellar remnants. If such interactions are confirmed, they could offer a broader context for understanding how similar nebulae form across different galactic environments. Advances in computational astrophysics are enabling the development of increasingly sophisticated simulations that attempt to recreate the conditions necessary for such a structured formation. These models incorporate factors such as stellar rotation, magnetic field dynamics, radiation transport, and binary gravitational effects. The goal is to determine whether a single dominant force is responsible for shaping the nebula or if multiple factors are working together in a complex interplay. Early results suggest that while radiation pressure and magnetic fields alone can produce organized outflows, the addition of a binary companion significantly enhances the likelihood of maintaining long-term symmetry. If a compact object is present within the system, it could further complicate the dynamics of the nebula. A neutron star or black hole companion could be influencing the surrounding material through accretion-driven winds or relativistic jets. These high-energy processes could create additional structure within the nebula, potentially explaining regions of enhanced brightness or density variations observed in different wavelengths. If future observations detect X-ray emissions or rapid fluctuations in radio signals, it may provide direct evidence of a compact remnant playing an active role in the system. Another aspect of interest is whether this nebula represents a unique evolutionary path or if it shares characteristics with other known structures that have been observed at different stages of development. If similar formations exist but have gone unnoticed due to unfavorable viewing angles, it could suggest that such ordered mass ejections are more common than previously thought. A systematic survey of structured nebulae using high-resolution telescopes could help identify additional examples, refining our understanding of the conditions necessary for their formation. The long-term future of the nebula remains uncertain, as its fate will largely depend on the evolution of its central star. If the star continues shedding mass at a steady rate, the surrounding structure may gradually expand and fade over thousands of years, blending into the interstellar medium. Alternatively, if the star undergoes a more dramatic transition, such as collapsing into a white dwarf, neutron star, or black hole, it could leave behind a compact remnant that continues to interact with the surrounding material. If this leads to periodic bursts of energy, the nebula may experience episodic reillumination, creating a variable emission profile that persists long after the initial mass ejection event. If a supernova does occur within the nebula, it could produce one of the most visually and scientifically interesting explosion remnants ever observed. The pre-existing structure would shape the way the supernova shockwave propagates, creating intricate patterns of glowing filaments and ionized gas. The resulting explosion could provide valuable data on how mass loss before core collapse affects the properties of the supernova itself, offering a real-world test case for theoretical models of stellar death. Regardless of its ultimate fate, this nebula remains an astrophysical anomaly that continues to challenge conventional understanding. Its striking symmetry, dynamic environment, and potential connection to high-energy astrophysical processes make it an ideal subject for continued study. The combination of observational data, theoretical modeling, and future technological advancements promises to unlock further insights into the mechanisms responsible for shaping such extraordinary cosmic structures. In the broader context of stellar evolution, this nebula highlights the diversity of pathways that massive stars can take as they approach the end of their life cycles. Whether it represents a transient phenomenon or a more persistent stage of mass loss, it serves as a reminder that the processes governing the formation and evolution of stellar remnants are more intricate than previously assumed. As research continues, each new discovery will bring us closer to understanding the fundamental forces that sculpt the universe's most fascinating and mysterious celestial objects. As more data is gathered, the intricate dynamics governing this structured outflow become clearer, yet many aspects remain elusive. The balance between stellar wind pressure, radiation forces, and gravitational interactions is delicate, and minor fluctuations in any of these variables could significantly alter the nebula's morphology over time. If its current shape is maintained for an extended period, it would suggest an ongoing regulating mechanism, possibly a combination of persistent mass loss cycles and external constraints imposed by either a magnetic field or a binary companion. A deeper understanding of the internal motion of the gas is crucial in deciphering whether the structure is static or evolving. If gas and dust are flowing outward at a uniform velocity, then the nebula is expanding symmetrically without significant turbulence. However, if regions within the outflow exhibit differences in acceleration, it may indicate that multiple processes are acting simultaneously. The presence of high-velocity streams, for example, could point to localized shock waves where ejected material interacts with remnants of previous stellar mass loss. If the star at the center is rotating rapidly, it could also be affecting the mass ejection pattern. Fast rotation alters the shape of the stellar atmosphere, making it more oblate and enhancing equatorial mass loss through centrifugal forces. This would naturally produce an extended disk or toroidal structure around the star, which could act as a guiding framework for the broader nebula. If rotation is a key factor, then future spectroscopic studies of the star's surface may reveal Doppler broadening effects, indicating differential velocity regions across its surface. The role of ionization fronts within the nebula is another aspect of interest. If the central star's radiation is continuously exciting the surrounding gas, it may be forming stratified layers where different elements are ionized at varying depths. This would lead to a multi-tiered composition where hydrogen, helium, oxygen, and heavier elements are distributed according to their ionization potentials. Understanding these ionization boundaries could provide insight into how far the star's influence extends and whether the outer regions of the nebula are still actively shaped by radiation or are merely residual structures from past eruptions. The possible presence of dust filaments or molecular clouds within the nebula suggests that complex interactions between gas phase elements and solid particles are occurring. Dust grains play an important role in astrophysical chemistry, acting as catalysts for molecule formation by providing surfaces where atomic interactions can take place more efficiently. If the nebula is rich in carbonaceous or silicate dust, it may indicate that material from the star is condensing into solid form, eventually contributing to the raw material for future planetary system formation. One key observational goal is to determine whether the nebula is optically thick or if it allows significant amounts of radiation to escape. If it is largely transparent at certain wavelengths, then light from the central star may be escaping in directed beams, influencing surrounding interstellar clouds beyond the immediate boundaries of the structure. This could result in faint emission regions detectable in infrared or radio wavelengths, providing clues about how the nebula interacts with the broader galactic environment. The possibility of a faint, extended halo surrounding the main structure is also being explored. Some nebulae exhibit diffuse outer layers, where lower density gas gradually transitions into the surrounding medium. If this system follows a similar pattern, then it may have an extended outer envelope that is not immediately visible in current observations but could be revealed through deep exposure imaging techniques. If such a halo is present, it may contain older material from earlier mass ejections, offering a more complete picture of the star's long-term evolution. Further study of light polarization within the nebula may also help in determining whether magnetic fields are contributing to its structure. If dust grains are aligned along a preferred axis, it could indicate that an underlying magnetic field is shaping the flow of ionized gas. Strong magnetic confinement could explain why material appears to be expanding in a highly organized manner rather than dissipating irregularly, as is typical in many other stellar outflows. High-resolution radio observations could provide additional evidence of magnetic influence by detecting synchrotron radiation, which occurs when charged particles spiral along magnetic field lines. The long-term monitoring of the nebula's brightness and shape will provide important clues about its future evolution. If no significant changes are observed over the coming decades, it could suggest that the system has reached a stable equilibrium, where forces acting within it counterbalance one another. However, if gradual shifts in emission intensity or structural features are detected, it may indicate that the nebula is still undergoing active reshaping, driven either by continued mass loss or external forces acting on the expanding shell. If the central star eventually transitions into a late-stage degenerate remnant, such as a white dwarf or neutron star, its interactions with the nebula may take on new characteristics. A cooling white dwarf would emit lower energy radiation, potentially altering the ionization structure of the nebula over time. If a neutron star or black hole forms, accretion of remaining material could generate episodic bursts of high-energy emissions, further complicating the evolutionary trajectory of the surrounding gas. With the advent of more sensitive astronomical instruments, including future space-based and ground-based telescopes, finer details of the nebula's composition and kinematics will become accessible. Multi-wavelength campaigns combining optical, infrared, radio, and X-ray data will allow researchers to construct an increasingly refined model of the processes governing this remarkable structure. By extending observational coverage to different regions of the electromagnetic spectrum, new physical interactions may be revealed, providing additional pieces to the puzzle of its formation and persistence. Understanding this nebula has broader implications beyond its immediate structure. If similar objects are discovered in different star-forming regions or near other evolved stellar systems, it could indicate that such formations represent a recurring phase in the life cycles of massive stars. This would provide new constraints on theories of stellar mass loss and the role of binarity, magnetic fields, and radiation pressure in shaping astrophysical outflows. Each discovery would bring us closer to understanding the universal principles that govern the transformation of stars and the lasting impact they leave on their environments. As research continues, the nebula remains a fascinating subject at the intersection of multiple astrophysical disciplines. Its structured appearance challenges traditional models, suggesting that either previously unrecognized mechanisms are at work or that known processes are operating in a more complex manner than currently understood. The insights gained from this system will not only refine our understanding of mass loss in evolved stars but may also influence broader concepts in astrophysics, from supernova progenitors to the formation of chemically enriched regions within galaxies. No matter what future observations reveal, this nebula stands as a striking testament to the intricate and often unexpected interactions that shape the cosmos. The persistence of such an intricate and symmetrical structure suggests that it is not merely a fleeting phase but a system governed by sustained forces. If the nebula were purely the result of a single explosive event, its features would have begun to dissipate in a more chaotic fashion over time. Instead, the defined edges and organized outflows indicate that ongoing mechanisms are reinforcing its structure, preventing it from dissolving into an irregular cloud. Understanding the nature of these stabilizing forces will provide crucial insights into how long such formations can persist and what role they play in the broader galactic ecosystem. One of the key aspects under investigation is whether the gas and dust within the nebula are interacting with interstellar magnetic fields beyond the immediate influence of the central star. If so, the entire system may be embedded within a larger-scale magnetized region that is influencing the way material is distributed. This would mean that its shape is not solely the result of internal stellar processes but is also being conditioned by environmental factors on a much larger scale. The interaction of expanding nebulae with the ambient galactic magnetic field is a relatively unexplored area of research, but it could have profound implications for understanding the formation of structured outflows in other astrophysical settings. The possibility that the nebula is part of a larger feedback loop within its local stellar neighborhood is another avenue of study. If mass loss from the central star is feeding surrounding molecular clouds, it could be triggering secondary star formation in nearby regions. In this scenario, the nebula is not just a byproduct of stellar evolution but an active participant in the recycling of matter, enriching the interstellar medium with heavier elements and influencing the next generation of star formation. If observations detect enhanced star-forming activity in adjacent regions, it would support the idea that evolved stars contribute more directly to galactic chemical evolution than previously assumed. Infrared imaging continues to reveal variations in dust grain size and composition, suggesting that material within the nebula is undergoing active processing. Some regions appear to contain larger, more complex carbonaceous compounds, possibly formed through prolonged exposure to ultraviolet radiation. If dust grains within the nebula have been altered by repeated ionization cycles, they may exhibit unique spectral signatures that could serve as a marker for similar objects elsewhere in the galaxy. By identifying the specific types of molecules present, researchers may be able to determine whether this environment is conducive to the formation of organic precursors to planetary systems. The thermal structure of the nebula is another critical factor in assessing its long-term stability. If the gas within it is being heated unevenly, localized instabilities may form, leading to subtle structural changes over time. High-resolution temperature maps created from multi-wavelength observations could reveal whether certain regions are cooling more rapidly than others, potentially setting the stage for future condensation of material. If dense clumps are forming within the nebula, they could eventually collapse under their own gravity, leading to the formation of new stellar objects. While this would be an unexpected outcome for a system of this type, it cannot yet be ruled out. The search for variability in the brightness of the central star remains ongoing. If the star exhibits periodic fluctuations in luminosity, it may indicate pulsational instabilities affecting its outer layers. These variations could, in turn, influence the mass loss rate, leading to episodic enhancements in the nebula's structure. If brightness changes are detected, correlating them with observed changes in the nebula's emission patterns could help establish a direct link between stellar activity and the evolution of the surrounding material. The outermost layers of the nebula are of particular interest, as they may provide a record of its earliest formation stages. If weak shock waves are detected propagating through the outer edges, it could suggest that the nebula is still expanding into previously undisturbed interstellar space. These shocks could be producing low-density filaments that are difficult to detect in optical wavelengths but may be revealed through radio observations. If such features are confirmed, they would provide valuable clues about the nebula's expansion dynamics and whether it is still actively interacting with its environment. One of the most significant remaining uncertainties is whether this structure represents a phase that other massive stars undergo or if it is an exceptional case. If similar objects exist but have not yet been identified, it could mean that such nebulae are more common than previously thought but remain undetected due to observational limitations. Systematic searches using next-generation telescopes with enhanced sensitivity in the infrared and radio bands may reveal whether this is part of a broader class of stellar outflows that have gone largely unrecognized. If the nebula is indeed a precursor to a supernova event, its surrounding structure may serve as a unique observational target when the explosion occurs. The interaction between the supernova shockwave and the pre-existing circumstellar material could produce intricate patterns of emission, allowing astronomers to witness the complex interplay of stellar remnants and nebular evolution in real time. The ability to study such an event would provide unprecedented insights into how mass loss influences the properties of supernova explosions, helping to refine models of core collapse dynamics. The continuing refinement of astrophysical models incorporating observational data from this nebula will lead to a better understanding of the forces shaping high-mass stellar environments. As computational capabilities advance, simulations will be able to incorporate increasingly detailed physical parameters, allowing researchers to test different formation scenarios and compare them directly to observational data. If a definitive explanation for the nebula's structure emerges, it will not only resolve one of the most intriguing astrophysical mysteries but also provide a framework for understanding similar objects that may be discovered in the future. Regardless of what new findings emerge, this nebula remains a compelling example of the complexity of stellar evolution and the diversity of structures that can arise from seemingly chaotic processes. Its continued study will provide valuable insights into how stars interact with their surroundings, how mass is redistributed throughout the galaxy, and how the final stages of stellar evolution shape the interstellar medium. Each new observation brings us closer to uncovering the full story behind this remarkable formation, revealing the intricate and often unexpected ways in which stars leave their mark on the cosmos. As research progresses, the long-term evolution of this nebula remains one of the most compelling unknowns. Whether its structure will remain stable for thousands of years or gradually dissipate into the surrounding interstellar medium is still unclear. If the forces maintaining its symmetry weaken over time, the well-defined edges may begin to blur as expanding gas disperses. However, if there are persistent shaping mechanisms, such as ongoing stellar mass loss, magnetic field interactions, or external pressure from surrounding interstellar clouds, the structure may remain largely intact for an extended period. Observations in multiple wavelengths continue to refine our understanding of the nebula's internal structure. Radio observations, for instance, are particularly useful in detecting cold gas components that may not be visible in optical or infrared light. If significant amounts of molecular gas are present, it could indicate that the outer layers of the nebula are cooling and condensing, which might lead to the formation of secondary features such as filamentary streams or localized high-density regions. These structures, if confirmed, would provide further evidence of ongoing interactions between stellar ejecta and the surrounding environment. The distribution of heavier elements within the nebula is also of interest. If enriched materials such as oxygen, nitrogen, and carbon are concentrated in specific regions, it could suggest that different layers of gas are expanding at different rates or that localized ionization fronts are influencing chemical processes. Detailed spectral analysis may reveal whether these elements were produced in earlier nuclear fusion cycles within the central star or if they are the result of more recent nucleosynthesis in an unstable stellar atmosphere. Another crucial factor in understanding the nebula's evolution is determining whether it is interacting with external gas flows from other nearby stellar sources. If the region around the nebula contains additional massive stars that are shedding material, their outflows could be influencing the expansion and shape of the structure. This would suggest that nebular symmetry is not solely dictated by the properties of the central star but is also affected by its galactic environment. If such interactions are detected, they could provide new insights into how massive stars shape their surroundings on a larger scale. The question of whether the central star is truly alone remains unresolved. The possibility of an unseen binary companion continues to be explored through precise radial velocity measurements and high-resolution imaging. If a compact object, such as a neutron star or white dwarf, is orbiting within the system, its gravitational effects could be contributing to the organized shape of the surrounding material. A binary scenario could also explain periodic mass ejection events, which would be consistent with the layered appearance of some regions within the nebula. The alignment of the structure with potential galactic magnetic fields is another factor under examination. If the nebula's shape is influenced by larger-scale magnetic interactions, it would suggest that it is not an isolated phenomenon but part of a broader network of interconnected astrophysical processes. If future measurements detect signs of external magnetic influence, it may support the idea that structured stellar outflows are not solely dictated by internal dynamics but can be modified by extrinsic forces acting on a galactic scale. If this nebula does eventually undergo a transformation due to a supernova explosion, the resulting remnant could provide a rare opportunity to observe how a pre-existing structured outflow interacts with a high-energy shockwave. Such an event would likely produce an asymmetric supernova remnant, with expanding material encountering dense regions in some directions while escaping more freely in others. This would create a highly complex emission pattern, providing valuable data on how circumstellar matter influences the outcome of core collapse events. Even if a supernova does not occur in the near future, the nebula's gradual evolution will offer important insights into how mass loss continues in late-stage stellar systems. Long-term observations will track changes in its brightness, expansion rate, and spectral properties, revealing whether the structure is gradually dispersing or if it remains dynamically active. If the nebula continues to exhibit stability over time, it may challenge existing theories of mass ejection and suggest that previously unrecognized stabilizing mechanisms are at work. Future telescopes, particularly those designed for high-resolution spectroscopy and polarization studies, will be instrumental in unraveling the finer details of the nebula's composition and motion. By studying variations in emission across different regions, astronomers may be able to determine whether specific forces, such as localized shock waves or radiation pressure differences, are influencing its evolution. These observations will help build a more comprehensive model of how massive stellar outflows develop and persist. This nebula remains a remarkable case study for astrophysics, not only because of its striking appearance but because of the numerous unanswered questions surrounding its origin, stability, and eventual fate. Whether it represents a rare phenomenon or an overlooked stage in stellar evolution, it challenges conventional assumptions and invites further exploration into the complexities of massive star systems. Each new observation brings us closer to a full understanding of the forces shaping the cosmos, demonstrating that even in an era of advanced astronomical technology, the universe continues to reveal mysteries that push the boundaries of human knowledge. As the study of this structured nebula advances, its significance extends beyond its immediate formation, hinting at broader astrophysical processes that govern the life cycles of massive stars. The long-term stability of its shape suggests that mass ejection is occurring in a controlled manner, possibly influenced by a combination of radiation pressure, rotational effects, and external constraints imposed by a larger galactic framework. The degree to which these forces interact remains an open question, but each new observational dataset refines our understanding of the mechanisms at play. Recent spectroscopic measurements have revealed variations in ionization levels across different regions of the nebula, suggesting that the central star's radiation is not evenly distributed. This could indicate that the star is experiencing rotationally modulated emissions, where different parts of its surface emit varying intensities of ultraviolet and X-ray radiation over time. If so, the asymmetry in radiation output could be influencing the density distribution of surrounding gas, reinforcing the structured shape by preferentially ionizing certain areas while leaving others relatively undisturbed. The search for a binary companion remains an ongoing effort, with continued radial velocity studies and high-resolution imaging campaigns aiming to detect any subtle gravitational influences that might suggest the presence of an orbiting secondary object. If a compact remnant, such as a neutron star or a white dwarf, is hidden within the system, it could be driving periodic outflows through mass transfer interactions. Even if no direct evidence of a secondary star is found, the possibility of past interactions with a now-merged companion remains a plausible explanation for the structured ejection pattern. Magnetohydrodynamic modeling suggests that if magnetic fields are present within the nebula, they could be acting as a stabilizing force, guiding ionized plasma along specific paths and preventing the structure from dispersing chaotically. If confirmed, this would provide new insights into how large-scale magnetic configurations contribute to the formation of highly organized stellar remnants. Future polarization studies will be crucial in determining whether aligned dust grains or synchrotron emission signatures indicate the presence of magnetic shaping. The discovery of molecular compounds in specific regions of the nebula provides further evidence of ongoing chemical evolution. The identification of carbon-rich molecules, possibly including complex organics such as polycyclic aromatic hydrocarbons, suggests that the nebula is not simply a passive stellar remnant but a dynamic chemical environment where high-energy radiation is continuously altering molecular structures. This has implications for the study of interstellar medium enrichment, as such nebulae may act as sources of prebiotic material that eventually contribute to the formation of planetary systems. Another aspect under examination is the thermal structure of the gas and dust within the nebula. If temperature gradients are detected, it could indicate localized heating effects caused by shocks or regions where high-energy radiation is penetrating deeper into the expanding layers. By mapping these temperature variations across different spectral bands, astronomers can better understand whether the nebula is undergoing a steady cooling process or if certain regions are being repeatedly reheated by external influences. Long-term monitoring efforts aim to determine whether the nebula exhibits subtle changes over time. If small-scale shifts in brightness or morphology are detected, they could signal ongoing interactions with external gas clouds or internal stellar variability influencing the surrounding material. If, on the other hand, the structure remains largely unchanged for decades, it would imply that the forces maintaining its shape are remarkably stable, challenging traditional models of nebular evolution. The broader implications of this research extend to the study of massive star populations in different galactic environments. If similar structured nebulae are discovered elsewhere, it would suggest that this is not an isolated phenomenon but rather a recurring phase in the late-stage evolution of certain types of stars. Systematic surveys using next-generation telescopes could reveal whether other examples exist, providing statistical evidence to support new theoretical frameworks. If this nebula eventually transitions into a supernova remnant, it will provide a unique opportunity to observe how a structured circumstellar medium interacts with an energetic explosion. The resulting supernova shockwave would propagate through the pre-existing outflows, creating intricate emission patterns and potentially leading to asymmetric expansion dynamics. Such an event would be invaluable for refining models of core-collapse supernovae and their interactions with surrounding material. Regardless of its future trajectory, this nebula remains one of the most fascinating astrophysical puzzles of recent times. Its highly ordered structure defies conventional expectations, prompting a re-evaluation of the processes governing stellar mass loss and outflow organization. Whether shaped primarily by binary interactions, magnetic confinement, radiation-driven winds, or a combination of multiple forces, it offers an unparalleled opportunity to study the interplay between stellar evolution and nebular dynamics. The continued investigation of this system will contribute to a deeper understanding of the fundamental principles that shape celestial structures, from the smallest dust grains to the largest-scale galactic formations. Each discovery adds another layer of complexity to our understanding of the cosmos, demonstrating that even in an era of advanced observational capabilities, nature continues to surprise and challenge our theoretical frameworks. The nebula remains a beacon of scientific curiosity, inviting further exploration into the hidden mechanisms that govern the life and death of stars across the universe. As research into this remarkable nebula advances, it continues to serve as a key astrophysical laboratory, revealing the interplay of multiple forces that govern the evolution of massive stars. Its near-perfect symmetry, long-term stability, and complex chemical composition challenge traditional models of stellar mass loss and nebular dynamics. While most nebulae form through chaotic processes, this structure suggests a level of organization that is difficult to explain through standard mechanisms alone. The persistence of its shape implies that self-regulating forces must be at work, reinforcing its geometry over time and preventing it from dissipating into an amorphous cloud. One of the most intriguing aspects of this system is its potential connection to broader astrophysical phenomena. If the nebula is shaped by a previously unknown feedback mechanism, it could offer insights into how large-scale magnetic fields, binary interactions, and stellar wind collisions contribute to nebular evolution. Some researchers propose that if the star is rotating at high speeds, the centrifugal forces could be influencing the way material is expelled, leading to an anisotropic outflow pattern. This could explain why mass ejections appear to be funneled along specific axes rather than expanding spherically, as is common in many evolved stellar systems. Infrared studies have revealed that the dust composition within the nebula is not uniform, with certain regions showing enhanced concentrations of complex molecules. This suggests that the nebula is not only a passive structure but an active site of chemical evolution, where high-energy radiation is triggering reactions that modify the molecular landscape over time. The detection of carbon-based compounds, including large polycyclic aromatic hydrocarbons, PAHs, hints at a potential connection between nebular environments and the formation of prebiotic molecules in space. If the conditions within the nebula resemble those found in protoplanetary disks, it could provide clues about the earliest stages of planetary system formation and how organic material is distributed across the galaxy. Another avenue of investigation involves mapping the expansion rate of the nebula's outer layers. If the velocity of the gas varies across different regions, it could suggest that multiple mass ejection events occurred at different times, each contributing to the layered structure. By analyzing Doppler shifts in the spectral lines of ionized gas, astronomers can reconstruct the three-dimensional motion of material within the nebula, determining whether it is undergoing uniform expansion or if internal forces are modifying its trajectory. If deviations from standard expansion models are detected, it could provide evidence for ongoing interactions with an unseen companion or an external pressure source shaping the outflow. The possibility that the nebula is part of a larger-scale galactic structure is also being explored. If the surrounding region contains other remnants of past stellar activity, it could indicate that the system is embedded within a dense stellar cluster, where multiple massive stars have contributed to shaping the environment. In this case, the nebula may not be an isolated formation but part of a network of interconnected astrophysical processes, where interactions between different stellar outflows have created complex patterns of gas and dust. Detecting such connections could provide valuable insights into how massive stars collectively influence the structure of their host galaxies, contributing to the enrichment of interstellar space with heavier elements and driving the formation of new stars. Another critical question is whether the nebula is in a stable or transitional phase. If it remains unchanged over long periods, it would suggest that the forces shaping it are self-sustaining, maintaining its geometry over extended timescales. However, if subtle shifts in brightness or morphology are observed, it could indicate that the nebula is evolving dynamically, either through continued interactions with its central star or through gradual dispersion into the interstellar medium. Monitoring these changes over time will help determine whether the nebula is a long-lived phenomenon or if it represents a fleeting stage in the late evolution of its progenitor. If a supernova were to occur within the nebula, it would provide an unprecedented opportunity to study how an explosion propagates through a highly structured circumstellar medium. Unlike typical supernova remnants, which often expand into relatively diffuse environments, this system would present a complex pre-existing structure that could dramatically influence the resulting shockwave dynamics. The interaction between the explosion and the nebula could lead to asymmetric ejecta patterns, unusual light curves, or the formation of intricate filamentary structures as ionized gas collides with denser regions of dust. If such an event were to be observed in real time, it would offer invaluable data on how massive stars end their lives and how their surrounding environments shape the final stages of their evolution. The presence of strong magnetic fields within the nebula remains an open question, but if confirmed, it could provide a crucial missing piece in explaining its structure. If the expelled gas is interacting with an external magnetized region, it could be following field lines that dictate its movement and alignment. High-resolution polarization studies will be essential in determining whether the observed symmetry is the result of magnetic confinement, offering new insights into how large-scale cosmic magnetic fields influence nebular dynamics. The future of research into this nebula will involve deeper investigations into its chemical composition, velocity distribution, and interactions with its surrounding environment. Advanced instruments such as the James Webb Space Telescope, JWST, Extremely Large Telescope, ELT, and Atacama Large Millimeter/Submillimeter Array, ALMA, will allow astronomers to probe deeper into its molecular and atomic structure, revealing details that were previously beyond the reach of observational technology. By combining data from multiple wavelengths, from radio to X-ray, researchers will be able to construct a comprehensive model of the nebula's evolution, identifying the forces responsible for its formation and predicting its long-term fate. This nebula remains one of the most extraordinary examples of how stellar mass loss can create highly ordered structures in space. Whether its symmetry is the result of binary dynamics, magnetic shaping, radiation pressure, or a combination of these factors, its existence challenges conventional theories of how stars interact with their surroundings. If it is part of a broader class of structured nebulae that have yet to be fully recognized, it could lead to a revision of current models of stellar evolution, highlighting previously unaccounted for processes that influence the final stages of a star's life. Regardless of what future discoveries reveal, this nebula stands as a striking example of the complexity of astrophysical systems. It demonstrates that even in an era of highly advanced astronomical technology, nature continues to present puzzles that defy easy explanation. Its study will not only deepen our understanding of individual stellar outflows but also contribute to a broader perspective on how stars shape the galaxies they inhabit. Each new observation brings us one step closer to unraveling the mysteries of this extraordinary formation, reinforcing the idea that the cosmos is far more intricate and dynamic than we ever imagined. As our understanding of this enigmatic nebula deepens, it becomes increasingly clear that its significance extends beyond a single remarkable formation. It is a testament to the intricate forces governing stellar evolution, challenging existing theories and prompting new questions about how massive stars interact with their surroundings. Whether its structure is the result of binary interactions, magnetic shaping, radiation-driven winds, or an interplay of multiple forces, it represents a rare and invaluable case study in astrophysics. The future of research into this system will rely on a combination of observational and theoretical advancements. With the next generation of telescopes, including the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, the Square Kilometre Array, SKA, and future X-ray observatories, astronomers will be able to probe deeper into the nebula's chemical composition, velocity distribution, and potential magnetic fields. High-resolution polarization studies will determine whether external magnetic influences are shaping its structure, while multi-wavelength spectroscopy will refine our understanding of its thermal dynamics and molecular complexity. If variations in brightness, expansion rates, or ionization levels are detected over time, they could provide key evidence of ongoing interactions within the system. Another avenue of exploration lies in the search for similar objects elsewhere in the galaxy. If other nebulae with comparable symmetry and structure are discovered, it could indicate that this is not a unique anomaly but part of a broader, yet previously unrecognized class of stellar outflows. Systematic surveys using deep-field imaging techniques may uncover additional examples, helping to establish the conditions necessary for such formations to occur. If no other similar structures are found, it will reinforce the exceptional nature of this nebula, making it a priority for continued study. Long-term monitoring will also be essential in determining the nebula's ultimate fate. If it remains stable over centuries, it would suggest that the forces maintaining its shape are self-sustaining, potentially revealing new physics governing mass loss in evolved stars. However, if it begins to change, whether through gradual dissipation, interaction with the interstellar medium, or the influence of an external shockwave, it may provide a rare opportunity to witness a transitionary phase in the evolution of a stellar remnant. If a supernova event occurs within this structure, the resulting shockwave could interact with the pre-existing nebula in a way that has never been observed before, offering unprecedented insights into how massive stars shape their surroundings both before and after their explosive deaths. Ultimately, this nebula serves as a reminder that even in an age of advanced astronomical instrumentation and sophisticated theoretical models, the universe still holds mysteries that defy easy explanation. It is a challenge to our understanding of stellar physics, a catalyst for new discoveries, and a window into the complex and dynamic processes that shape the cosmos. As technology advances and new data become available, each observation brings us closer to unlocking the full story behind this extraordinary formation, ensuring that its legacy will endure as one of the most intriguing astrophysical puzzles of our time. Whether it remains a stable, structured beacon in the cosmos or transforms dramatically in the coming centuries, its study will continue to inspire curiosity, push the boundaries of astrophysical research, and expand our knowledge of the fundamental forces that govern the universe. The Antennae galaxies, also known as NGC 4038 and NGC 4039, represent one of the most stunning examples of galactic interaction ever observed. These twin celestial entities, engaged in an intricate cosmic dance, have fascinated astronomers and enthusiasts alike for centuries. Their remarkable structure, shaped by powerful gravitational forces, illustrates the chaotic beauty emerging when galaxies collide and merge over millions of years. Often referred to as the cosmic antennae, this pair lies approximately 60 million light-years away in the constellation Corvus. Originally separate spiral galaxies, they are currently experiencing a slow yet captivating merging process, generating extraordinary stellar phenomena. Their elongated tidal tails, from which the antennae derive their distinctive name, extend far into space, filled with gas, dust, and stars expelled during their gravitational encounter. What makes this celestial pair even more intriguing is its role as a cosmic laboratory. Within their turbulent interior, astronomers have identified regions of vigorous star formation known as starburst zones. These stellar nurseries, fueled by gas and dust compressed during the collision, produce stars at a rate significantly surpassing typical galactic levels. Studying this entwined system enables researchers to better comprehend galaxy formation and evolution, revealing fundamental processes shaping the broader universe. The detailed structure of this galactic embrace is not only visually breathtaking but scientifically priceless. Observations from the Hubble Space Telescope and other advanced observatories have unveiled intricate features within individual star clusters. Some of these clusters rank among the most massive and luminous ever recorded, containing millions of stars densely packed into relatively compact regions. These findings offer astronomers insights into extreme environments similar to those prevalent in the early universe, when galactic mergers occurred more frequently. As these interwoven spirals continue their prolonged collision, gravitational forces trigger impressive phenomena. Massive clouds of molecular gas become compressed, igniting the formation of hot, young stars. These stars emit intense ultraviolet radiation and powerful stellar winds, shaping the surrounding interstellar medium and sustaining cycles of star birth and destruction. The dynamic interplay between gravity, radiation, and stellar winds generates a continuously evolving cosmic landscape, highlighting the universe's immense complexity. This celestial collision also provides a preview of the distant future awaiting our own galaxy. Astronomers anticipate a similar encounter between the Milky Way and Andromeda Galaxy in approximately 4 billion years. By analyzing interactions like the antennae, scientists gain valuable knowledge about future developments in our galactic neighborhood. Although galaxy mergers are not rare occurrences, the antennae offer an exceptionally vivid illustration of their transformative impact. The gravitational ballet of these interacting galaxies serves as a powerful reminder of the immense forces governing the cosmos. These two celestial companions, once separate entities with distinct identities, are now slowly merging into a unified structure. Though their encounter appears violent and chaotic, this cosmic collision ultimately creates a new galaxy, enriched by the remnants of its predecessors. This galactic fusion exemplifies the universe's extraordinary capacity for both destruction and creation, dismantling old formations to give rise to new cosmic wonders. The interacting pair has long captured the attention of astronomers studying multi-wavelength astronomy. Observations across the electromagnetic spectrum, from radio waves to X-rays, have uncovered various aspects of their intricate interaction. For example, X-ray analyses have revealed the existence of supermassive black holes at the center of each galaxy, as well as hot gas energized by supernova explosions and stellar winds. These energetic phenomena offer valuable insights into the physical processes at work during galaxy collisions. Beyond their scientific importance, this cosmic duo inspires awe and wonder worldwide. Striking images captured by powerful telescopes have become iconic representations of the universe's profound beauty and complexity. Their expansive tidal tails and vibrant starburst regions evoke curiosity, reminding us of the vast mysteries existing beyond our home planet. Continuing research into these merging galaxies constantly pushes the boundaries of our understanding. As observational technologies evolve, astronomers will explore this remarkable pair in even greater detail, providing new insights into the dynamics of galaxy mergers and cosmic evolution. This celestial pair thus stands as a powerful testament to humanity's ongoing scientific pursuit and the endless potential for discovery in the universe. The eternal embrace of these colliding giants narrates a captivating story of transformation and cosmic renewal. It reveals the immense gravitational forces shaping the universe, depicting stars forming, evolving, and eventually dying as galaxies transform over billions of years. By investigating these galaxies, we gain deeper insight into cosmic interconnectedness and humanity's small yet meaningful place within the vast cosmos. These luminous cosmic dancers inspire us to continue exploring fundamental questions about existence. Sometimes poetically named the celestial whirlpool, this captivating system vividly demonstrates the immense drama unfolding in the universe. Their cosmic encounter began billions of years ago, not through a sudden explosive impact, but in a slow, graceful gravitational attraction. These two once independent spiral galaxies initiated an elaborate cosmic choreography, fundamentally reshaping their internal structures and star populations. Each tidal arm extending into interstellar space tells its own story of galactic upheaval. These elongated streams of gas and dust, stretching tens of thousands of light-years, are not merely remnants of destruction but hold immense creative potential. Eventually, these cosmic streams will condense into new stars and planetary systems, making this dynamic region a spectacular stellar nursery. This galactic factory symbolizes the universe's ultimate recycling, where even destructive forces fuel new creation. For astronomers, this interacting pair provides a remarkable opportunity, offering clues about galactic history and destiny. Consider, for instance, the fascinating starburst regions scattered throughout these intertwined galaxies. These stellar nurseries form stars at a rate 10 times greater than the Milky Way. Observations of these regions allow scientists to study shock waves produced by gas collisions, unlocking secrets of galactic evolution in the early universe. Infrared and radio observations uncover even more hidden features, including enormous reservoirs of molecular gas, the foundational ingredient for star formation. Although galactic collisions disrupt the orderly movement of gas, they also compress it in select regions, initiating star formation through powerful cosmic chain reactions. This process produces a brilliant tapestry of new stars, some destined to shine brightly for millions of years, while others end their brief, turbulent lives as supernovae. Supernovae occur abundantly in the stellar bridge connecting the two galaxies, a region of densely packed stellar populations. These dramatic stellar explosions release massive energy, heating surrounding gas and accelerating cosmic cycles of renewal. Supernovae also produce heavier elements such as iron and gold, dispersing these critical building blocks across space. Eventually, these elements enrich subsequent generations of stars, planets, and potentially life itself. Thus, these colliding galaxies represent not just a cosmic encounter, but a stellar forge, crafting fundamental materials for future cosmic ecosystems. One particularly intriguing aspect of this tidal symphony is its insights into galactic cores. Each galaxy possesses a central supermassive black hole encircled by swirling gas and stars. As the galaxies merge, these black holes will eventually unite in a monumental cosmic event, forming an even larger singularity. This ongoing process offers astronomers a unique chance to study black hole dynamics, including mergers that send gravitational waves rippling through spacetime itself. Consequently, this spectacular interacting system is more than visually magnificent, it serves as a gateway to revolutionary physics. The galactic mosaic, as some prefer to call these interacting galaxies, challenges our perception of cosmic time. The merging process, dramatic from our perspective, actually unfolds across hundreds of millions of years. Throughout most of its history, the galaxy's transformation remains invisible to the human eye, yet advanced simulations enable astronomers to reconstruct the timeline of their encounter. By comparing current observations with these simulations, scientists predict the future shape of the resulting elliptical galaxy, which will likely shed the spiral arms characteristic of its original components. Yet this stellar tempest is not only about vast, galactic-scale events. On smaller scales, it provides crucial insights into the behavior of individual star clusters during mergers. Many stars born from this turbulent environment are clustered into massive globular formations containing millions of stars. These clusters, resilient survivors of cosmic upheaval, will likely orbit the new galaxy for billions of years. Studying them grants astronomers important clues regarding conditions prevalent during the earliest stages of galaxy formation, as globular clusters often preserve evidence from the universe's infancy. On the outskirts of these interacting galaxies, where tidal tails stretch like ethereal threads into intergalactic space, lies another mystery, the ultimate fate of ejected gas and stars. Some of this material may escape entirely, joining the broader intergalactic medium, while other portions may eventually return to the galaxies themselves. This continuous interplay between creation and loss underscores the transient nature of cosmic structures. Observing this spectacular galactic collision resembles watching the opening act of a play spanning billions of years, yet the themes it conveys remain timeless. Chaos and order, destruction and renewal, stellar birth and death, all reflect universal cycles playing out across every scale. These merging cosmic giants remind us of the interconnected nature of existence, from microscopic atoms to enormous superclusters. As telescopes reveal the galactic entanglement, we witness more than a mere collision of galaxies. Instead, we glimpse the very mechanisms that have shaped the universe since its inception. In their remarkable complexity, these colliding galaxies embody the universe's boundless creative potential. They form an eternal symphony of motion, light, and transformation, prompting us to ponder humanity's role within the infinite cosmic fabric. Their slow evolution toward a unified structure reminds us that in the vast expanse of space, no object truly exists in isolation. Every star, galaxy, and atom contributes to a grander cosmic narrative, shaped by gravity, energy, and time. The cosmic harmony of chaos, as these interacting galaxies are also known, creates a visual narrative spanning countless light-years, interweaving past, present, and future. Their interaction sheds light on processes that have defined galaxy evolution since the universe's earliest days. Each tidal tail, starburst region, and star cluster within this cosmic dance tells a chapter of this larger universal story, a story marked by growth, transformation, and powerful cosmic forces. One of the most striking features of these stellar collision twins is their tidal tails, immense streams of stars and gas extending outward into space. These tails, sculpted by gravitational forces during the galaxy's spiraling approach, resemble threads pulled from a cosmic tapestry. Amid this apparent chaos lies hidden order, as tidal tails serve as highways transporting gas and stars to new regions, fostering the formation of future celestial systems. Within these extensive tidal streams roam rogue stars, celestial wanderers ejected from their galactic homes during the collision. Scattered through intergalactic space, these lonely travelers bear witness to the galaxy's turbulent past. Astronomers exploring these gravitationally formed streams have also identified disrupted star clusters and protosystems, potential seeds for new astronomical objects, offering valuable clues about the collision's dynamics. At the heart of this merging marvel lie the cores of NGC 4038 and NGC 4039, set on an inevitable collision course. This imminent merging of galactic cores holds monumental significance. Each galaxy harbors a supermassive black hole, containing millions of solar masses. Eventually, as their host galaxies coalesce, these black holes will merge, producing powerful gravitational waves capable of rippling through spacetime itself. This spectacular cosmic event ranks among astrophysics' most extreme phenomena, offering critical insights into gravitational wave science. Yet black hole mergers are not the only dramatic changes unfolding at the center of these interstellar titans. Dense concentrations of gas and dust undergo intense compression, triggering bursts of rapid star formation. This intense activity reshapes galactic cores, fueling feedback loops wherein young stars and subsequent supernova explosions heat surrounding gas, thereby influencing future star formation. Thus, these central regions become epicenters of simultaneous creation and destruction. Another captivating aspect of this tidal cosmic duo lies in how their collision alters not just physical structures but chemical composition as well. Vigorous starburst activity triggered by the encounter synthesizes heavy elements, or metals in astronomical terms. These metals, forged within stars and dispersed by supernovae, enrich interstellar gas, establishing conditions favorable for planetary formation and potentially even life. In this way, these merging galaxies are actively preparing the stage for future worlds. Beyond visible wavelengths revealing swirling chaos, multi-wavelength observations unveil even more hidden phenomena. Infrared astronomy penetrates dense dust clouds, revealing obscured star-forming regions. X-ray observations expose high-energy processes, such as black hole accretion disks and supernova remnants. Combined, these varied perspectives enable astronomers to develop a comprehensive understanding of processes occurring within this remarkable galactic interaction, ranging from microscopic scales to vast cosmic dimensions. Observing this cosmic tapestry also allows us to peer into the distant past. When telescopes capture their light, we observe events as they appeared approximately 60 million years ago, given the finite speed of light. Thus, these galaxies serve as cosmic time capsules, presenting snapshots of ancient cosmic events. This temporal dimension deepens their intrigue, emphasizing the immense scales of time and space shaping our universe. The future of these interacting galaxies proves equally fascinating. As their merger progresses, individual identities gradually dissolve, and spiral arms disappear, leaving behind a more amorphous elliptical galaxy. This future structure, enriched by star formation and black hole activity during the merger, embodies cosmic transformation on the grandest scale. Although the complete metamorphosis will require hundreds of millions of years, its inevitability serves as a potent reminder of the universe's cyclical nature. In studying these gravitational titans, astronomers gain valuable insights into the future of our own galaxy. The Milky Way is destined for a collision with the Andromeda Galaxy in about 4 billion years. Although this future seems unimaginably distant, observing the cosmic dance between these galaxies helps scientists predict the processes shaping such colossal encounters. By examining this ongoing interaction, we glimpse the formation of a new elliptical galaxy, gradually stripped of the delicate spiral structures that once defined its predecessors. This celestial ballet of galaxies is more than just a scientific curiosity, it inspires awe across the globe. Striking images of their swirling arms and vibrant regions of star formation have become iconic representations of the universe's beauty and complexity. They invite contemplation of the vastness of space, provoking reflection on our place within this cosmic expanse. These interacting galaxies represent endless cycles of creation and destruction, mirroring the universal dynamics of existence itself. Whether through telescopic observations or scientific analyses, they continually offer opportunities for discovery and wonder. They serve as a vibrant testament to the universe's limitless creativity, a symphony of gravity, light, and motion that inspires generation after generation. The intricate dance of NGC 4038 and NGC 4039 unfolds slowly, each detail, tidal tails, brilliant star-forming regions, and chaotic collisions, forming chapters in an epic tale of cosmic transformation. These galaxies remind us that the universe itself is an artist, painting with gravity, time, and light. As these celestial dancers continue their gravitational interaction, waves of star formation ripple outward. Massive, short-lived stars ignite quickly, ending in supernova explosions that scatter newly created elements into space. These stellar fireworks enrich surrounding gas clouds, fueling future generations of stars in an endless cycle of destruction and rebirth. Amidst this violent environment emerge globular star clusters, surprisingly stable formations containing millions of stars. These clusters, forged in turbulence, often survive the collision, orbiting the resultant galaxy as relics of its past. Examining these ancient stellar groupings provides clues about conditions present during the earliest phases of galaxy evolution. Much of the drama unfolding in the cosmic ballet occurs beyond visible wavelengths. Infrared observations reveal hidden regions of star formation concealed by dust, while X-rays unveil high-energy phenomena, such as supermassive black hole activity and supernova remnants. These multi-wavelength views allow scientists to construct comprehensive portraits of galactic evolution, from the smallest structures to the largest processes. The gravitational interplay between NGC 4038 and NGC 4039 is gradually drawing their cores closer, setting the stage for an eventual merger of their supermassive black holes. This monumental event will produce gravitational waves powerful enough to ripple through spacetime, representing one of the universe's most dramatic phenomena and a crucial area of astrophysical research. Yet the dramatic transformations extend beyond their cores. Gas and dust compressed by gravitational forces trigger intense star formation, fueling feedback loops where supernova explosions reshape their surroundings. This interaction transforms galactic cores into centers of simultaneous creation and destruction, continually reshaping their environments. Another remarkable outcome of this collision is the chemical enrichment of the interstellar medium. Heavy elements produced during starburst events are scattered throughout the galaxies, creating favorable conditions for planet formation and, potentially, life itself. Thus, these merging giants are not merely evolving, they are laying the groundwork for future celestial worlds. Beyond the visible spectrum, observations in infrared and radio wavelengths unveil hidden star-forming regions obscured by dense dust, while X-rays reveal high-energy phenomena such as supernova remnants and black hole accretion disks. This rich, multidimensional view offers astronomers deeper understanding of the cosmic forces shaping these celestial structures. When observing these galaxies, we look 60 million years into the past due to the finite speed of light, turning our telescopes into cosmic time machines. This temporal dimension adds depth, reminding us of the immense scales defining our universe. Ultimately, as these galaxies continue merging, their original identities will fade. The delicate spiral arms will give way to a featureless elliptical galaxy, home to billions of stars born through past turmoil. Although the transformation unfolds slowly, it underscores the cyclical nature of cosmic evolution, highlighting that even vast cosmic structures are transient and interconnected. The collision between these celestial giants provides astronomers a unique laboratory, offering an unparalleled opportunity to witness the dynamics that shape the cosmos. Each tidal stream, starburst, and cluster within their intricate dance narrates part of the universal story, one of growth, transformation, and cosmic forces. In their eternal cosmic performance, these galaxies remind us that, in the vastness of space, nothing stands truly alone. Every star, galaxy, and atom is interconnected, bound together in a universal narrative crafted by gravity, energy, and time. The tidal symphony of these interacting galaxies extends beyond their visible boundaries. Long, graceful tidal tails stretch into intergalactic space, forming bridges linking the merging galaxies with the broader cosmic environment. Filled with stars, gas, and dust, these tails are vibrant zones where material ejected during collision encounters the surrounding interstellar medium. Occasionally, such debris can even coalesce into entirely new structures, known as tidal dwarf galaxies. These nascent systems represent the universe's remarkable ability to create amidst chaos. Astronomers studying the gravitational ballet of NGC 4038 and NGC 4039 also gain deeper insights into stellar life cycles. Massive, short-lived stars born in starburst regions emit intense ultraviolet radiation and stellar winds, sculpting the surrounding gas clouds into intricate patterns of brightness and shadow. These stars end dramatically in supernova explosions, enriching the interstellar environment with heavy elements, vital building blocks for future stars, planets, and potentially life. This interplay between destruction and creation within the celestial collision underscores a fundamental cosmic balance. Though these galaxies are engaged in violent upheaval, they simultaneously sow the seeds for new generations of celestial bodies. Material cast out during their encounter will eventually cool, condensing into fresh stars and planetary systems, perpetuating the universe's timeless cycle of renewal. The merger of NGC 4038 and NGC 4039 into a unified elliptical galaxy will mark the culmination of this extraordinary transformation. Stripped of their elegant spiral arms, the new galaxy will be a monument to cosmic evolution, housing a supermassive black hole formed from the fusion of its predecessors' cores. Richly infused with elements produced throughout their interaction, this new celestial structure stands as a testament to gravity's power as the sculptor of galaxies. Astronomers continually find inspiration in this eternal embrace, exploring profound cosmic mysteries through these interacting giants. They serve as windows into galactic evolution, both past and future, including insights into our own galaxy's eventual encounter with Andromeda billions of years from now. Powered by human curiosity and advanced technology like the Hubble Space Telescope, ALMA, and the James Webb Space Telescope, researchers have uncovered unprecedented details of these merging galaxies. Each new discovery adds layers of understanding about cosmic dynamics, enriching our appreciation for the complexity and beauty of the universe. These galaxies, often poetically described as the luminous chaos, inspire awe worldwide. Striking images of their swirling arms and brilliant star clusters remind us of the vast majesty of space, prompting questions about humanity's place within this infinite narrative. They challenge us to imagine beyond our own experience, to seek answers to profound existential questions. The infinite tapestry woven by these cosmic entities continues to unfold, dynamically shaped by gravitational, temporal, and energetic forces. They are living records of universal processes, every tidal stream, starburst, and molecular cloud offering clues to the fundamental mechanics of cosmic evolution. Within this galactic cascade, complexity reigns. The gravitational interactions between these galaxies fling material into luminous arcs spanning tens of thousands of light-years. Far from mere destruction, these tidal streams carry the seeds for new celestial systems and even entire galaxies. Embedded within them lie tidal dwarf galaxies, miniature cosmic laboratories providing valuable insight into how the universe's earliest structures may have formed. Closer to the heart of these celestial titans, star formation erupts with extraordinary intensity. Immense clouds of molecular gas, compressed and heated by gravitational forces, become stellar nurseries igniting stars at rates vastly exceeding typical galactic activity. These dynamic regions radiate brilliantly across the electromagnetic spectrum, offering astronomers rich data about star formation processes, stellar evolution, and the dynamic forces shaping galaxies. Thus, this cosmic interaction remains a profound symbol of transformation, creativity, and renewal, continually reshaping our understanding of the universe itself. Within these starburst regions, the most massive stars burn brightly but briefly, ending their short lives in dramatic supernova explosions after only a few million years. These supernovae are not merely spectacular cosmic displays, they play crucial roles in galactic evolution. The explosions release enormous energy, heating nearby gas and propelling powerful stellar winds outward. These winds reshape the interstellar medium, forming shock fronts and cavities that can either ignite new waves of star formation or halt the process entirely. This intricate cycle of cosmic feedback defines the nature of this extraordinary galactic forge. Yet supernovae accomplish more than merely rearranging the surrounding gas, they also enrich it chemically. Heavy elements like carbon, oxygen, and iron, created within the cores of massive stars, are dispersed by these explosions throughout the surrounding environment. These elements serve as critical ingredients for future planets and possibly life itself. In this way, these stellar laboratories function as cosmic alchemists, seeding the universe with building blocks necessary for future worlds, continuing a process ongoing since the earliest epochs. The hidden realms within these celestial giants are equally intriguing. Infrared and radio observations reveal vast reservoirs of cold molecular gas, key fuel for star formation, concealed within the chaotic regions of these galaxies. Invisible to optical telescopes, this gas is fundamental to their evolutionary future. As gravitational forces compress and heat this material, it provides essential raw material for new stellar populations, ensuring these cosmic entities will shine brilliantly for millions of years. Simultaneously, X-ray telescopes have uncovered intense activity within the cores of these galaxies, detecting powerful radiation from accretion disks surrounding supermassive black holes. These galactic nuclei actively consume vast amounts of matter, radiating intensely as material spirals inward. Far from passive observers, these black holes actively shape their host galaxies' evolution through powerful gravitational and energetic feedback mechanisms, influencing star formation on galactic scales. As this interstellar duo moves slowly toward an inevitable merger, gravitational interactions will intensify dramatically. Over hundreds of millions of years, these galaxies will increasingly intertwine, becoming ever more distorted and losing their unique identities. The delicate spiral arms that once distinguished them will disappear, replaced by a chaotic and amorphous structure. In the merger's final act, their central supermassive black holes will collide, emitting powerful gravitational waves rippling through spacetime itself. This ultimate merging will give birth to a new elliptical galaxy, combining the stars, gas, and massive black hole remnants of both predecessors. The resulting galaxy, smoother and more spherical, will stand as a magnificent testament to cosmic transformation, enriched by elements created during its formation. It will provide fertile ground for continued stellar and planetary birth, echoing the ongoing cycles of cosmic renewal. For humanity, this celestial event is more than a distant curiosity, it symbolizes profound cosmic inspiration. It reminds us of the universe's vast scale, the immense forces that shape it, and the beauty that emerges from these powerful processes. These galaxies invite contemplation of countless other cosmic dramas unfolding across the universe, each as dynamic and intricate as the dance we observe here. Through their gravitational interplay, these cosmic titans mirror universal cycles of life, death, and renewal, demonstrating that destruction often serves as a catalyst for creativity. They teach us to embrace change, find beauty amid chaos, and marvel at the infinite possibilities inherent in the cosmos. As astronomers continue exploring this tidal symphony, every new observation deepens our understanding of galactic evolution and the universe itself. Each discovery adds layers of complexity, further revealing the boundless creativity of the cosmos. These galaxies serve as cosmic masterpieces, inspiring awe and curiosity, and inviting us on an endless journey of discovery across space and time. This endless cosmic saga, as these galaxies are often described, continues to unfold on timescales beyond human comprehension. Locked in their gravitational embrace, they offer a vivid example of the universe transforming chaos into order, destruction into creation, and turmoil into harmony. This grand narrative, expressed through gravity and starlight, resonates profoundly across the cosmos. The galaxy's tidal tales remain among their most dramatic features. These luminous streams, composed of stars, gas, and dust, reach like cosmic bridges into intergalactic space. Within these immense arcs, isolated stars journey as cosmic wanderers, carrying ancient light across the darkness, bearing witness to their turbulent origins. Moreover, the tidal arms host intricate knots of gas and dust, where star formation actively begins. These regions, compressed by gravitational forces, serve as stellar nurseries, incubating the next generation of celestial bodies. By studying these nurseries, astronomers gain insights into star formation's earliest moments, discovering conditions essential for the birth of stars and planets. These tidal streams thus represent more than mere relics of galactic disruption, they are vibrant zones of cosmic rebirth. At the heart of this galactic fusion ballet, the galaxy's supermassive black holes are spiraling toward an eventual, dramatic collision. When they finally merge, the event will unleash immense bursts of gravitational waves, ripples in spacetime detectable across vast cosmic distances. These waves will carry echoes of the galaxy's violent dance far into the universe, allowing astronomers to study in detail the dynamics of such monumental interactions. Yet, even now, long before the black holes collide, the cores of these celestial entities are astonishingly active. Their central regions, known as active galactic nuclei, shine brilliantly, powered by intense radiation emitted from hot accretion disks. As gas and dust spiral into the gravitational wells of these massive black holes, enormous amounts of energy radiate outward, illuminating the galaxy's chaotic transformations from within. Simultaneously, a starburst tempest rages across these interacting galaxies, fueled by the massive compression and collision of molecular clouds of gas. Powerful waves of star formation ripple through their structures, igniting millions of new stars that blaze brightly across the cosmos. Many of these newly born stars are massive and short-lived, shaping their surroundings with intense ultraviolet radiation and stellar winds. Their rapid, spectacular deaths in supernova explosions scatter heavy elements, carbon, oxygen, iron, into surrounding space, enriching the galaxy's environment and paving the way for future planetary systems. This intricate balance between creation and destruction within this intergalactic forge exemplifies the universe's cyclical nature. Though these galaxies appear locked in a violent dance, their collision plays a vital role in cosmic evolution. Without such tumultuous events, the universe would lack the ingredients necessary for rocky planets, oceans, organic molecules, and ultimately life itself. As the tidal titans merge, their once distinct spiral forms dissolve into more chaotic and amorphous shapes. Eventually, the elegant spirals will disappear, leaving behind a smoother elliptical galaxy. This new entity will embody the legacy of its predecessors, home to countless stars and enriched with materials forged through the turbulence of their interaction. At its center will lie a unified, massive black hole, the remnant of their dramatic collision and a testament to gravitational power. The elliptical galaxy born from NGC 4038 and NGC 4039 will itself evolve, possibly encountering other galaxies over billions of years, continuing the cycle of mergers and interactions that characterize the cosmic web. With each new collision, it will grow and change, continually shaping its legacy across cosmic timescales. For astronomers, these celestial titans offer infinite avenues of discovery. Every observation uncovers fresh details, from the intricacies of tidal tails to the mechanisms of star formation and black hole interactions. Advanced instruments like the James Webb Space Telescope promise even deeper insights, opening new windows into their complex evolutionary history. Yet these galaxies serve humanity beyond mere scientific curiosity, they inspire awe and contemplation. Their breathtaking images, vivid and dynamic, challenge us to consider the vastness of the cosmos, the incredible forces at play, and our own place within its grand narrative. Their cosmic collision mirrors universal themes of renewal and transformation. They demonstrate vividly that destruction is not an end but rather the beginning of something new. These galaxies invite us to embrace change, to recognize beauty amid chaos, and to marvel at the universe's endless potential for creativity. As research continues into this ongoing tidal symphony, each discovery enriches our understanding of cosmic evolution and fuels our collective imagination. These galaxies represent a living masterpiece of cosmic creativity, sparking wonder and curiosity among all who gaze upon them. Their story is still unfolding, inviting humanity on a timeless journey through space and imagination. The endless saga of NGC 4038 and NGC 4039 continues to evolve on scales beyond human comprehension. Their gravitational embrace symbolizes the universe's extraordinary ability to shape chaos into order, destruction into creation, and turmoil into harmony. Told through gravity and starlight, their narrative echoes throughout the cosmos, offering humanity a window into profound cosmic forces. Among their most captivating features are the galaxy's tidal tales, ethereal, luminous bridges extending into the intergalactic void. Within these glowing streams, isolated stars wander as cosmic nomads, expelled from their original homes by gravitational upheaval. Despite their isolation, these stars carry forward the ancient starlight of their origins, journeying endlessly through space. Embedded within these expansive tidal arms lie intricate knots of gas and dust, stellar nurseries actively forming new stars. These regions, compressed by gravitational disruptions, provide fertile grounds for future celestial bodies. Studying these nurseries grants astronomers insights into star formation's earliest stages, illuminating conditions necessary for star and planet formation. Far from mere remnants of collision, these tidal structures signify vibrant rebirth and renewal within the cosmos. At the heart of this galactic fusion ballet, the interaction between the cores of NGC 4038 and NGC 4039 vividly demonstrates gravity's immense power on a cosmic scale. Each galaxy's center, anchored by a supermassive black hole, is gradually spiraling inward due to their mutual gravitational pull. The future collision of these black holes will unleash a dramatic surge of gravitational waves, ripples in spacetime traveling across vast cosmic distances, detectable by advanced observational instruments, carrying echoes of this spectacular galactic merger. Yet, even now, far before that ultimate black hole merger, the activity around the galaxy's cores remains captivating. Surrounding each central black hole is a glowing accretion disk composed of gas and dust spiraling inward, heated to extreme temperatures and radiating energy across the electromagnetic spectrum. These active galactic nuclei, AGN, shine brilliantly, illuminating their surroundings and marking the cores as the most energetic zones of these celestial interactions. The starburst tempest triggered by this merger is another vital chapter in their cosmic narrative. Waves of intense star formation ripple throughout the combined galactic structures, giving rise to vast populations of massive, short-lived stars. These young stars emit intense ultraviolet radiation and powerful stellar winds, reshaping the surrounding interstellar gas into intricate bubbles and filaments. When these massive stars explode as supernovae, they scatter heavy elements, carbon, oxygen, iron, across the interstellar medium, setting the stage for the formation of future stars and planetary systems. The dynamic interplay between creation and destruction in this cosmic forge symbolizes the cyclical nature of universal evolution. Though violent, the collision is essential, enriching the cosmos with the elements necessary for life. Without such interactions, the universe as we recognize it would not exist. As the galactic titans continue their gravitational dance, their distinctive spiral structures become increasingly disrupted, morphing into a more amorphous, elliptical form. This eventual elliptical galaxy, smoother and spherical, will embody the legacy of its predecessors. It will be enriched by elements produced during the collision and house a unified supermassive black hole at its core, serving as a permanent testament to the transformational power of gravity. Over billions of years, this newly formed elliptical galaxy will continue to evolve, potentially merging with neighboring galaxies, perpetuating cycles of galactic evolution. Each subsequent merger contributes further to its mass, complexity, and cosmic legacy, integrating it into the broader story of the universe. For astronomers, this gravitational ballet offers endless avenues of exploration and discovery. Each observation reveals deeper complexity, from tidal interactions to star formation mechanisms and black hole dynamics. Cutting-edge instruments, such as the James Webb Space Telescope, promise even more detailed exploration, providing unprecedented insight into the galaxy's transformative processes. Beyond their scientific value, these galaxies embody profound cosmic inspiration. Their beauty, dynamism, and intricate structure capture human imagination, prompting reflection on the universe's vastness and majesty. They challenge us to consider our place within an infinitely larger narrative, exploring questions about existence itself. In their collision, these celestial titans reflect the universal cycles that govern all creation. They illustrate that destruction is not an end but a vital stage of transformation, enabling renewal and growth. They inspire us to see potential within chaos, recognizing the endless possibilities offered by the cosmos. As research progresses into this remarkable tidal symphony, each discovery deepens our understanding of the universe's workings, revealing its boundless creativity. These merging galaxies stand as living masterpieces, stimulating wonder and curiosity, encouraging us to journey further into cosmic mysteries. The ongoing saga of NGC 4038 and NGC 4039, often described as an eternal cosmic ballet, continues to captivate astronomers and dreamers alike. Their gravitational embrace illustrates vividly how the universe transforms chaos into harmony, turmoil into creation. Expressed through starlight and gravitational forces, this grand cosmic narrative resonates profoundly, offering humanity unique insights into the immense forces shaping our universe. Their distinctive tidal tales, spectacular streams of stars and gas, stretch outward into intergalactic space like luminous threads. Within these streams, ejected stars wander as cosmic travelers, carrying memories of their violent origins. Yet these tales are also rich sites of renewal, containing clusters of gas and dust actively forming new stars, proof of the universe's remarkable resilience and ongoing creative power. Thus, this galactic collision remains a testament to cosmic evolution, forever reminding us that even amid chaos, the universe continues to renew itself, weaving order from disorder and beauty from destruction. Even as the tidal titans approach their ultimate merger, the internal processes unfolding within them continue to yield new scientific insights. Infrared observations have uncovered hidden pockets of star formation obscured by dense dust clouds invisible to optical telescopes. These findings, enabled by advanced observatories like the James Webb Space Telescope, provide astronomers with detailed views of the galaxy's most active and dynamic regions, revealing the intricate mechanisms driving their transformation. Simultaneously, radio telescopes map the distribution of cold molecular gas, the essential building blocks of new stars, illustrating how this vital resource is redistributed and consumed during galactic collisions. The galactic tempest occurring within these merging galaxies provides an extraordinary opportunity to study feedback mechanisms crucial to galactic evolution. The combined energy released by young stars, supernova explosions, and active galactic nuclei shapes their structure and behavior. In some regions, this powerful feedback compresses gas, igniting further waves of star formation, while elsewhere it expels material entirely, suppressing future star birth. Understanding this delicate balance is essential for deciphering galaxy evolution throughout the universe. Ultimately, the product of this profound cosmic symphony of destruction and creation will be a massive elliptical galaxy, markedly different from the spiral structures of NGC 4038 and NGC 4039. This future elliptical galaxy, smooth and luminous, will be enriched by heavy elements synthesized during the collision, setting the stage for the formation of new planetary systems and potentially life-bearing worlds. For humanity, observing the eternal dance of these galaxies is both a compelling scientific endeavor and a powerful reminder of our cosmic connection. Their complexity, dynamic evolution, and breathtaking beauty encourage us to ponder the vastness of the universe, the immense forces shaping it, and humanity's place within this grand narrative. As their saga unfolds, these galaxies remind us of universal interconnectedness. The processes at play here mirror those that have shaped countless other galaxies, including our Milky Way. They highlight a shared cosmic history, written in stars, gas, and gravity, revealing the universe as a dynamic, ever-evolving tapestry, where even violent collisions give rise to new order and beauty. In this context, the galactic renaissance of NGC 4038 and NGC 4039 transcends mere destruction. It symbolizes resilience, transformation, and endless cosmic creativity, inspiring humanity to explore, imagine, and embrace the infinite possibilities of existence. Their narrative is ongoing, continuously inviting us to discover new cosmic wonders and embrace the mysteries beyond our current understanding. This timeless orchestration, an interplay of gravity, energy, and matter, is an enduring narrative of complexity and wonder. The intertwined galaxies serve as cosmic laboratories, displaying dramatic processes fundamental to galaxy formation and evolution. Their story of destruction and renewal unfolds over hundreds of millions of years, offering profound insights into universal forces at work across space and time. As these celestial giants draw ever closer, their spiral structures are gradually disrupted and reshaped into immense tidal streams extending far into intergalactic space. Within these luminous tidal tails, stars and dense gas clumps coalesce into new stellar systems, demonstrating vividly how cosmic collisions repurpose galactic debris into new celestial life. These tidal tails also give rise to tidal dwarf galaxies, miniature, independent star systems formed swiftly from collision debris. These dwarf galaxies provide astronomers with invaluable insights into rapid galaxy formation processes, resembling conditions prevalent during the early universe, when galactic mergers were far more common. At the heart of these merging galaxies, powerful gravitational forces compress gas and dust into supermassive star-forming regions. Here, bursts of stellar creation ignite, producing massive, short-lived stars that illuminate their surroundings with intense ultraviolet radiation. Eventually, these stars end their brief lives in dramatic supernova explosions, enriching the surrounding gas with essential heavy elements like carbon, oxygen, and iron, ingredients crucial to planet formation and life. Thus, even amidst chaos, this extraordinary galactic collision embodies renewal, illustrating that destruction is often a necessary precursor to creation. These interacting galaxies symbolize the universe's endless potential for transformation, urging us to recognize beauty and possibility within cosmic upheaval. The invisible symphony captured in wavelengths beyond human sight reveals even deeper insights into the forces shaping these colliding galaxies. Infrared observations unveil dense clouds of molecular gas concealed within the tidal tails and galactic cores. Shrouded by dust that obscures visible wavelengths, this molecular gas serves as the essential raw material for star formation. Mapping its distribution and flow enables astronomers to trace material pathways, uncovering how new stars and star clusters form in the cosmic interplay. Simultaneously, X-ray observations illuminate the high-energy phenomena unfolding in the cores of NGC 4038 and NGC 4039. These energetic emissions arise from hot, diffuse gas heated by supernova explosions, as well as from luminous accretion disks orbiting supermassive black holes at each galaxy's heart. These massive black holes, millions of times more massive than the Sun, gradually spiral inward toward each other as the merger progresses. Their eventual collision will unleash powerful gravitational waves, ripples in spacetime that provide a unique opportunity to study the extreme physics of black hole mergers. The eventual destiny of these gravitational dancers is clear: they will unite to form a single, cohesive galaxy. This newly formed elliptical galaxy, lacking the elegant spiral arms once defining NGC 4038 and NGC 4039, will nonetheless stand magnificent and luminous. Richly infused with heavy elements created throughout the collision, and anchored by a single, unified supermassive black hole, it will serve as a monumental testament to gravitational forces and cosmic resilience. Yet, the saga of these tidal giants does not conclude with their merger. The newly born elliptical galaxy will continue evolving, potentially encountering other galaxies, initiating fresh rounds of cosmic interactions. Each new encounter will enrich its complexity and deepen its history, reinforcing the notion that galaxies are never static but are continuously reshaped by cosmic processes. For humanity, observing this timeless celestial dance offers profound inspiration. The galaxy's complex structures, dynamic interactions, and striking beauty remind us of the universe's immense scale and intricate nature. They invite us to explore beyond our limited perspective, inspiring us to seek answers to fundamental questions about existence itself. These merging galaxies represent far more than distant astronomical phenomena. They symbolize the universe's boundless capacity for creativity, transformation, and renewal. Their story embodies the eternal cycles that govern existence, reminding us of the interconnectedness between chaos and order, destruction and rebirth. Studying their ongoing evolution deepens our understanding of the cosmos and highlights the beauty inherent in universal transformations. The grand finale of NGC 4038 and NGC 4039, as they spiral toward the climax of their cosmic performance, is not merely an ending but a profound metamorphosis, one whose impact will reverberate across cosmic timescales. This concluding act encapsulates the very essence of universal evolution, illustrating vividly how destruction creates opportunities for new cosmic order. As their epic story approaches this pivotal moment, the galaxies offer an enduring lesson about the infinite cycle of life, death, and renewal that shapes the cosmos itself. In the coming hundreds of millions of years, these two galaxies will become increasingly intertwined. Their once distinct spiral arms, already disrupted and stretched into magnificent tidal streams, will further dissolve into an intricate mass of stars, gas, and cosmic dust. The elegant structures that each galaxy once possessed will transition into a more amorphous shape as their unique identities gradually fade. Yet, hidden within this apparent chaos is a deeper purpose. This collision is not merely the destruction of two galaxies, it is the birth of something entirely new. Central to this cosmic transformation will be the eventual merger of their supermassive black holes. These enormous gravitational giants, millions of times the mass of the Sun, currently spiral slowly toward each other. As their paths inevitably converge, they will unleash powerful gravitational waves, ripples propagating through spacetime itself. This black hole merger, one of the most energetic phenomena in the universe, will be detectable by advanced gravitational wave observatories in the distant future, marking the ultimate climax of the galaxy's transformative dance. The resulting galaxy, likely elliptical in shape, will possess immense mass and luminosity. It will lack the delicate spiral arms that once characterized its progenitors, yet its magnificence will remain undeniable. Instead, its stars will form a smooth, spherical halo, shaped by the gravitational forces that forged it. This elliptical galaxy will combine and carry forward the heavy elements created during its tumultuous formation, elements such as carbon, oxygen, and iron, essential ingredients for future generations of stars, planets, and possibly even life itself. This newly formed unified giant will preserve echoes of its turbulent past through its numerous globular clusters, dense, ancient groupings of stars created during the peak of the collision star-forming activity. Each cluster, harboring millions of stars, will orbit the elliptical galaxy as enduring relics of its dramatic origins. Within these clusters, stars and their planetary systems may one day become havens for life, thereby extending the galaxy's legacy in ways we cannot yet imagine. As this elliptical galaxy settles into its new cosmic form, it will continue to evolve over billions of years, interacting with neighboring galaxies, repeating the cycle of mergers that defines galactic evolution. Each future encounter will add layers of complexity, stars, gas, and dark matter, ensuring its story continues indefinitely. The cosmic legacy of these merging galaxies extends far beyond their physical structure. By studying them, astronomers gain critical insights into universal processes, how gravitational forces sculpt galaxy structure, how starbursts enrich interstellar space, and how supermassive black holes shape their environments. These galaxies serve as a crucial benchmark for understanding galaxy mergers, offering a living example of cosmic cycles at work. Beyond their scientific importance, these celestial entities inspire awe and curiosity, challenging humanity to envision scales beyond ordinary experience. Their complexity, evolving structures, and captivating beauty encourage us to reflect upon the universe's vastness and our interconnectedness with all cosmic phenomena. They remind us of the profound power of human exploration and discovery, urging us to look beyond our small planetary home and imagine the endless possibilities of the cosmos. As their ancient light travels millions of years across the cosmos to reach our telescopes, these celestial giants illustrate the profound relationship between time and distance in the universe. Observing them allows us to glimpse events from a distant past, highlighting the intricate connection between time, space, and our understanding of cosmic evolution. These merging galaxies deliver a timeless message of transformation, resilience, and renewal. They teach us that destruction often contains the seeds of future creation, embodying the universe's remarkable ability to forge beauty and complexity from chaos. These cosmic interactions remind us that nothing is static. Galaxies, stars, and even entire cosmic structures continually evolve, reshaped by gravitational forces, star formation, and powerful cosmic events. Their journey across millions of years serves as a powerful metaphor for humanity's place within the greater cosmic story. Just as galaxies are reshaped by gravitational forces, so too is our existence interconnected with the same universal processes that govern celestial bodies. The elements that make up our world were formed in the hearts of stars born and dispersed during events like these dramatic galactic mergers. The final chapter of these celestial companions is not merely an ending, it signifies the start of a new cosmic era. In their luminous aftermath, a new elliptical galaxy will emerge, embodying the unity forged from the collision of distinct cosmic entities. This future galaxy will carry the enriched legacy of its progenitors, providing fertile ground for future stars, planetary systems, and possibly life. As we gaze upon their distant light, we glimpse both past events and future possibilities, a future continually shaped by the same gravitational forces and stellar processes unfolding before our eyes. These galaxies stand as living symbols of cosmic potential, eternal reminders that even within chaos, the universe remains an ever-renewing tapestry of endless possibility, inspiring humanity to explore, imagine, and marvel at the wonders of existence. The term Eye of God is often associated with celestial phenomena, most notably the Helix Nebula, NGC 7293. This planetary nebula, located approximately 650 light-years from Earth in the constellation Aquarius, has captivated astronomers and the general public alike due to its striking resemblance to a human eye. However, beyond its visual appeal, the Helix Nebula serves as a crucial subject for scientific investigation, offering insights into the life cycle of stars and the dynamics of interstellar matter. This nebula represents the final stages of a sun-like star's evolution. When a star exhausts its nuclear fuel, it expands into a red giant before shedding its outer layers, forming a luminous cloud of ionized gas. The central remnant, a white dwarf, emits ultraviolet radiation, causing the ejected material to glow. The result is a stunning display of concentric shells of gas, rich in hydrogen, oxygen, and nitrogen. The intricate structure of the nebula, shaped by stellar winds and radiation pressure, reveals the complex interplay between a dying star and its surrounding environment. Observations of this so-called cosmic eye have been instrumental in advancing our understanding of stellar death. Infrared imaging from telescopes like the Spitzer Space Telescope has allowed astronomers to analyze the composition of the nebula, detecting molecules such as carbon dioxide and silicates, essential building blocks for planetary formation. Meanwhile, the Hubble Space Telescope's high-resolution images have provided a detailed view of its intricate filaments and knots of gas, remnants of the star's outer layers interacting with the interstellar medium. The celestial iris is also a valuable laboratory for studying the transition of matter from stars back into the cosmos. As the nebula disperses over thousands of years, the elements it contains will eventually contribute to the formation of new stars, planets, and potentially even life-bearing worlds. This cyclical nature of stellar material underscores the interconnectedness of cosmic evolution. Beyond the Helix Nebula, other nebulae resembling an astral pupil exist throughout the universe, each offering unique insights into astrophysical processes. The Cat's Eye Nebula, NGC 6543, in the constellation Draco, for example, displays a highly complex structure, with multiple shells and a turbulent interior shaped by a binary star system. These observations suggest that planetary nebulae, despite their name, are far more intricate than early astronomers had assumed. From a broader perspective, The study of these so-called universal oculus structures is vital for understanding the fate of our own Sun. In approximately 5 billion years, our star will undergo a similar transformation, shedding its outer layers and leaving behind a dense white dwarf. By analyzing nebulae like the helix, astronomers can predict how this process will unfold, offering a glimpse into the distant future of our solar system. Furthermore, the galactic lens concept extends beyond optical astronomy. Radio and X-ray telescopes have detected emissions from planetary nebulae, revealing energetic interactions between stellar remnants and their environments. These multi-wavelength observations help scientists piece together the puzzle of stellar evolution, uncovering processes that shape the universe at both microscopic and cosmic scales. The fascination with the heavenly gaze is not limited to professional astronomers. Public interest in these formations has been fueled by their striking imagery, often featured in popular science publications and space agency releases. The Helix Nebula, in particular, has been dubbed the Eye of God in cultural and artistic interpretations, symbolizing the vastness and mystery of the cosmos. As technology advances, new observational methods will allow scientists to further probe the depths of these stellar eyes. Upcoming space missions, such as the James Webb Space Telescope, promise to uncover finer details of nebular structures, shedding light on the physics of dying stars and their role in the cosmic cycle. By continuing to explore these celestial formations, we not only deepen our understanding of astrophysics but also reinforce humanity's connection to the universe. The ethereal vision, as seen in nebulae resembling a celestial eye, represents more than just the aesthetic marvel of the universe. It is a gateway to profound astrophysical insights. As observational techniques evolve, astronomers continue to unravel the complexities hidden within these cosmic structures, shedding light on the processes governing stellar evolution, interstellar chemistry, and the intricate balance between destruction and creation in the universe. One of the most intriguing aspects of the spectral gaze is the role planetary nebulae play in the chemical enrichment of the cosmos. Stars function as nuclear forges, synthesizing elements through fusion reactions over millions or billions of years. However, the true dissemination of these elements occurs during the final stages of a star's life. The Helix Nebula, like other similar structures, is rich in heavy elements such as carbon, oxygen, and nitrogen, materials that will eventually be incorporated into new generations of stars and planetary systems. Without this process, the fundamental building blocks of life would not exist, reinforcing the notion that planetary nebulae serve as crucial links in the cosmic cycle of matter. Recent observations using spectroscopic analysis have provided deeper insight into the composition of the celestial observer. By analyzing the emitted light at different wavelengths, astronomers have identified complex molecules and dust grains within these nebulae. The presence of polycyclic aromatic hydrocarbons, PAHs, organic molecules that form in the cooling gas of planetary nebulae, suggests that such regions may contribute to the organic inventory of the interstellar medium. This discovery has significant implications for astrobiology, as it indicates that the ingredients for life may be widely distributed throughout the universe, seeded by dying stars. Beyond their chemical contributions, the cosmic sentinel structures offer a glimpse into the physics of stellar winds and radiation-driven dynamics. The shaping of planetary nebulae is influenced by multiple factors, including the stellar wind from the progenitor star, magnetic fields, and even potential interactions with unseen companion stars. High-resolution imagery has revealed asymmetric structures, suggesting that many of these nebulae are not formed in isolation but are instead sculpted by gravitational interactions and external forces. For example, observations of the Galactic Observer using radio telescopes have unveiled the presence of collimated outflows, narrow, high-velocity streams of gas extending from the central star. These outflows, sometimes appearing as jets or bipolar lobes, provide evidence that the central white dwarf may have undergone interactions with an unseen companion, influencing the final distribution of expelled material. Such findings challenge earlier models that depicted planetary nebulae as simple, spherical shells and instead reveal a far more dynamic and chaotic process. Furthermore, the astronomical eye plays a role in the broader galactic ecosystem. The material ejected from these nebulae does not simply dissipate into the void, instead, it enriches surrounding molecular clouds, regions where new stars are born. This continuous recycling of stellar material ensures that each generation of stars contains heavier elements than the previous one, gradually shaping the chemical composition of galaxies over cosmic timescales. The study of these structures is poised for a major leap forward with the deployment of next-generation telescopes. The James Webb Space Telescope, JWST, with its unprecedented